Hello, today I am going to be talking about task-oriented grasping with point cloud representation of objects. The motivation behind this work is to provide robots with the ability to grasp objects and perform tasks that require applying a specific motion for successful execution of a task. Consider the task of operating a screwdriver or turning a doorknob. In both cases, we grasp the object to give them motion or apply a force and/or a moment about an axis. Consider the task of pivoting a Cheez-It box using a robot and an eye-in-hand perception system. The region where the object should be grasped depends on the axis of pivot. Even if multiple candidate grasps are provided to the robot, the suitability of the grasp depends on the pivoting axis, and good grasps for one pivoting axis may be bad for another axis. Therefore, our goal is to perform grasp synthesis while considering the motion to be imparted to the object for successful task execution. The first key challenge is to use a mathematical representation of a task which considers the motion to be imparted. The second challenge is that since environments are not engineered for robots, we may only have partial view of the object while grasping. For example, with the eye-in-hand configuration, we have a partial view due to self-occlusion, so we only obtain a partial point cloud. Now let us look at the geometric structure of a few common tasks. Common tasks such as opening a drawer or a drawer can be represented as a single constant screw motion about a particular axis. The main advantage of this representation is that it satisfies the kinematic motion constraints associated with a particular task. Tasks like pouring involve manipulating non-articulated objects like cups whose motion is not constrained by any joint. However, the constraints placed on the cup while pouring can be segmented into a sequence of constant screw motions. Thus, tasks with both articulated and non-articulated objects can be represented as a sequence of constant screw motions. This is motivated by Chazal's theorem. From Chazal's theorem, it is implied that any rigid body motion can be approximated arbitrarily closely by a sequence of constant screw motions. Now, our problem statement can be written as, given a point cloud representation of an object and a unit screw representing the desired constant screw motion, compute a grasping region for an antipodal grasp such that the grippers after grasping the object can apply the desired constant screw motion to the object. Our key contributions are: we have formalized the notion of task-oriented grasping as grasping for providing a sequence of constant screw motions. Secondly, we have developed a novel algorithm that uses the desired motion and a partial point cloud of an object as an input to compute a grasp for the desired motion. Our approach can be outlined as follows. Using the notion of task and a task-dependent grasp metric from our previous work, we use a neural network to approximate a function for predicting the grasp quality metric on the 3D bounding box of the object point cloud. The 3D bounding box, along with the approximated metric values, are used to generate a good grasping region on the object point cloud. The generated grasping region can then be used to compute antipodal grasps. Therefore, our approach does not require any manually labeled data or a grasping simulator. We have evaluated our approach in simulation as well as using real objects. Here are some of the results on simulated data. The yellow color denotes the ideal grasping region. The task screw is shown in red. The constant screw motion considered here is pure rotation about the task screw. Here are some results for real point clouds obtained from an RGBD camera. Exploiting the screw geometric structure of motion allows us to couple grasp synthesis with motion planning approaches developed using the same. We have evaluated this using a robot to perform the tasks of pivoting, pouring, and operating a screwdriver.